Hey, honors pre-calc. Today we are going to be doing lesson 5.4, Trig, applications and models. We're going to be asking the question, how do trig functions apply to real world applications or real world scenarios? And we'll be modeling real world periodic scenarios using sinusoidal functions. We're going to have a little bit of taste of a reminder of how trig can be applied to triangles. And then we're going to move into simple harmonic motion, which you had a little bit of a preview of already. Here's something that we will be able to do. A swimming pool is 20 meters long and 12 meters wide. The bottom of the pool is slanted so that the water depth is 1.3 meters at the shallow end and 4 meters at the deep end. Find the angle of depression of the bottom of the pool. So we'll be able to do questions like that. Real quick, before I switch over to the notes, I just wanted to bounce back here because I said the word sinusoidal, which you may not know. And that's just kind of like an adjective form of, like a sine function. So it's a function that follows that wave pattern that a sine function has. That's a fancy way of saying it. All right, so let's switch over to the notes. All right, so here are the notes. You can see at the top, we have the definition for simple harmonic motion. We're going to come back to this when we get to the second set of examples. For now, we're just going to look at applications involving right triangles. And this should, for the most part, feel like review because we've talked about all this before. In fact, right triangles are the first place that you see trig. So it's just a matter of kind of reminding ourselves that this is still an application of these same trig functions that we've used in many different ways since then. So let's take a look at letter A. Solve a right triangle ABC, where angle C is a right angle. The measure of angle A is 34.2 degrees, and the length of side B is 19.4. So this is just kind of getting us back in the mindset of right triangles rather than an actual application. The next three problems will be examples of applications with right triangles. So let's just set up a right triangle, first of all. And you can see angle C is the right angle, so I'm going to label that as C, and I'm just going to label A and B as either of the other two angles. This is just going to be a rough sketch, so it doesn't really matter where the A and B are, but I have that angle A is 34.2 degrees. And side B, so remember that's across from angle B, so the side over here is 19.4. So that's our setup. The question says to solve the right triangle. So we have to remember that the phrase solving a triangle means finding all the length of every side and the measure of every angle. So I'm going to, just to make sure I don't miss any of those, I'm going to write it out neatly as capital A, B, and C, and then lowercase a, b, and c. And I'm going to make sure I fill in this whole box before I finish. So I already know that angle C is 90 degrees and angle A is 34.2 degrees. And I know that side B is 19.4. And I just have to finish filling this in. So I would, first of all, notice that we have two of the three angles. And I know that in a right triangle or in any triangle, the three angles add up to 180 degrees. So I'm going to do 180 minus 90 minus 34.2, and I'm going to get the angle B is 55.8 degrees. So now I'm just missing two more sides, side A and side C. Side A is going to be this one down here, and side C is going to be the hypotenuse. So let me see. I'm going to choose to take advantage of the angle 55.8. which was angle B. So I'm going to let this be my theta here, and I'm going to use tangent. There are ways you could do sine, cosine, or tangent to solve this. I'm going to do tangent of 55.8 degrees. So I've picked my kind of starting angle, and tangent is opposite over adjacent. So it's going to be 19.4 over the adjacent side, which is across from angle A. So it's going to be lowercase a. Now, the way that I just explained that, I started by saying I was going to use tangent. You wouldn't really want to do that. You would start by saying, okay, I picked an angle. I'm going to go with the 19.4 and side A. And since that's the opposite and the adjacent side to this angle, I'm going to think about SOHCAHTOA. And tangent is the TOA, right? Tangent would be opposite over adjacent. That's the two sides I have, so that's what we want to use. So now we're going to solve this. So I'm going to multiply the a to the left side and then divide by the tangent. So we end up with a equals 19.4 over tangent of 55.8 degrees. And the next step would just be to type this into my calculator. I'm going to make sure that I'm in degree mode, and I end up with approximately 13.2. Since everything in this question has one decimal place, I feel comfortable rounding to one decimal place here. So we got lowercase a is 13.2. And now I can tell that my diagram is kind of trash because side A looks longer than side B, but it's actually shorter. But doesn't matter, as long as we have a right triangle. That's the important part here. And then side C. So we could do, SOHCAHTOA again, but I'm just going to notice, oh, I already have two sides. And in a right triangle, I know that a squared plus b squared equals c squared. Pythagorean theorem. So we can just use that to find the value of c. So we end up with 13.2 squared plus 19.4 squared equals c squared. And when I square, add, and then square root, I end up with a c of 23.5. And there we go. In a right triangle, the hypotenuse is always the largest or longest side length, and that is true in this case, so it worked. Okay, let's keep going. Letter B, a safety regulation states the maximum angle of elevation for a rescue ladder is 72 degrees. The fire department's longest ladder is 110 feet. What is the maximum safe rescue height? So I'm going to do here is sketch some height that we're going to be finding. And we have a ladder that has a maximum angle of elevation of 72 degrees. So that means that if we sketch our ladder like this, angle of elevation always means from the horizontal up. I could even write that in here if we wanted. Angle of elevation means from the horizontal up to the line. Okay, so that means this angle in here is our 72 degrees. And the longest ladder is 110 feet. So the question is, if this 110-foot ladder is put at a 72-degree angle of elevation, how high vertically does it go? And we can figure that out using SOHCAHTOA. So let's think about this. We are going to have some trig function of 72 degrees equals a fraction. I'm going to want to use the 110 and the h because I'm trying to solve for h. So if I think of the 72 degrees as our theta, the h is the opposite, and the 110 is the hypotenuse. So if I think about SOHCAHTOA, opposite and hypotenuse are part of the SOH, S-O-H, and that means sine. So we're going to do sine of 72 degrees equals h over 110. And we can solve this. So I am going to multiply both sides by 110. So we get h equals 110 times the sine of 72 degrees. And I'm going to make sure I'm in degree mode on my calculator, type this in, and I'm going to round to one decimal place, and I'll get 104.6 feet. Okay, let's keep going. At a point 200 feet from the base of a building, the angle of elevation, we know what that is, to the bottom of a smokestack is 35 degrees, whereas the angle of elevation to the top is 53 degrees. Find the height of the smokestack alone. So this question is a little bit complicated. See if you can tell already what this diagram should look like or what's really going on here. But in this problem, we have some sort of a building, and it has a smokestack on top. I'm not exactly sure how wide the smokestack would be, but it's something like that. And the reason I'm drawing it on the edge is because we're going to be a distance of 200 feet from the building. And from this position, it's saying the angle of elevation to the bottom of the smokestack is 35 degrees. like that. And the angle of elevation to the top of the smokestack is 53 degrees. Sorry if you mix up numbers, because now we have 35 and 53. But we're going to have to work hard to keep that straight. So now the question is, what is the height of the smokestack alone? So we are going to have two different trig functions that we'll have to evaluate with two different triangles. So let's think about this. Let me see if I can pull out a different color. First thing we're going to look at is just this inner right triangle, which I'm going to shade in red right here. And that we are going to find the height of the building without the smokestack using SOHCAHTOA, and we have the 35 degrees and the 200 that we can rely on here. Then we're going to look at the larger triangle that's still a right triangle. So I'm going to make that purple here. Sometimes purple looks black in my camera, so not sure if you'll be able to tell, but hopefully you can tell it's different than the other colors. Okay. And that larger triangle encompasses a smaller one, but that'll give us the height of the building and the smokestack together. So then once we have that height and the height of the building, we can subtract them to get the height of just the smokestack. So I will keep my color coding here, and let's find the inner triangle first, the red one. So we're going to have the 35 degrees, and we're interested in this, which I'm going to call H1. And the 200, that's the opposite and the adjacent. So that's going to be tangent of 35 degrees equals the opposite over the adjacent. And I can solve that by multiplying by 200. And that's going to be approximately 140.0 if you use your calculator. And I'll switch to purple for the other part. And we have the angle 53 degrees, and we're interested in this extended side, which I'm going to call H2, the whole height. And we still have that same 200 as our base of our triangle. So that's going to be tangent again, because we have opposite and adjacent to the 53 degrees. So we're going to have tangent of 53 degrees equals H2 over 200. So we have H2 equals 200 times tangent of 53 degrees. We can again type that into our calculator, and we'll end up with 265.4 feet. And so the height of the smokestack alone is going to be the purple length minus the red length. So it'll be 265.4 minus 140.0. It's going to give us a final answer of 125.4 feet. And there we go. Letter D. A swimming pool is 20 meters long and 12 meters wide. The bottom of the pool is slanted so that the water depth is 1.3 meters at the shallow end and 4 meters at the deep end. Find the angle of depression. So that's kind of the opposite of the angle of elevation. Angle of depression always goes from horizontal down to the line. So I'm going to write that right here. Of the bottom of the pool. Okay, so let me show you what I mean here. So let's create a sketch. This is going to be a swimming pool. I'm going to be showing you what it looks like from the side. And I'm going to try my best to make this look 3D. We'll see how it works. Okay. Okay. So this top right here is the surface of the water. And like most swimming pools, it gets deeper as you go. And it doesn't like stay shallow for a while and then get deep like some pools. This pool specifically has a slant the entire bottom of the pool. And we want to know the angle of depression, the amount the top rotates downward here. So if we thought of a straight horizontal line at the shallow end of the pool, the question is, what is the angle here of depression from the horizontal down to the slant of the bottom of the pool? So that's what we're looking for there. Think of that red line as being like on our end of the pool, the end that's closest to us with all the solid lines. Anyway, okay, so let's try this. So I have some numbers I can fill in here. The swimming pool is 20 meters long and 12 meters wide. The bottom of the pool is slanted so that the water depth is 1.3 meters at the shallow end and 4 meters at the deep end. Find the angle of depression. So what I'm going to do here is just think about this as my right triangle. And in that right triangle, if I think about it two-dimensionally, the top is just going to be that length of the pool of 20 meters. And over here, I can find this length too, because the shallow end has a depth of 1.3, the deep end is 4. So if I subtract them, I should get just the red length. So 4 minus 1.3 is going to be 2.7. And now I have the opposite and the adjacent, and I'm just looking for the angle. So we have the tangent of some theta is opposite over adjacent. And remember, on your calculator, you want to make sure that you are in degree mode. I've been saying that every single time. And to calculate this, we would do second tangent, which we now know what that graph looks like for arctan or inverse tangent. But we're actually just going to plug in the 2.7 over the 20. And we get 7.688. I'm just going to round that to 7.69 degrees. So there we go. So that was our review of right triangle trig. We're going to move then into simple harmonic motion. So there was a whole bunch of information thrown at you in a video about simple harmonic motion from Crash Course. You don't need to know most of the things in that video, but it was cool to see like the examples and how simple harmonic motion played into, the movement on a bridge. I like that application there. But anyway, before we even get to reading all of this, what I would like us to do is just go back and look at the definition in the first place. Simple harmonic motion is a point that moves on a coordinate line. It's said to be in simple harmonic motion if its distance from the origin at time t is given by some sort of a sine or a cosine curve. Typically, if it's up-down motion, we would use sine. If it's left-right motion, we would use cosine. And it's going to be d for distance equals a times sine of omega t. And this is just kind of switching up the variables from when we looked at the transformations. You will not have to memorize any of these different types of variables that are used in here, but a and omega are real numbers, and omega has to be greater than 0. The motion has amplitude, absolute value of a, which we know, period of 2 pi over omega, because omega is just taking the place of the b. And frequency, that's a new term. Frequency is just the reciprocal of the period. The frequency tells you how many periods happen per unit of time. So it would be like, if it was like 4, it might mean it bounces up and down 4 times in a second or something like that. We'll see that a little bit on the back. So let's try to apply this. A ball is bobbing up and down on the end of a spring. Suppose that 10 centimeters is the maximum distance the ball moves vertically upward or downward from its equilibrium or rest position. The time it takes for the ball to go from its positive max position to its negative maximum position and back is 4 seconds. From this, the period would be 4 seconds and the amplitude would be 10 centimeters. Write the equation for the simple harmonic motion of the ball and determine the frequency of this motion. So if we wanted to draw a diagram here, we have a ball on the end of a spring, something like that. The ball, 10 centimeters is the maximum distance the ball moves vertically upward or downward. And so we could move up 10 or down 10 from that center position. So you have to think that this ball is bouncing up and down here, and a sine curve is going to be showing us that motion over time. So we're going to start with the formula D equals A times sine of omega t. It's important that we don't just make that look like a W. So you usually have like an extra loop in the middle to show that it's not just a W, it's an omega. And in this question, it's pretty straightforward that the amplitude is 10. We go a maximum distance of 10 away from the center. So without any, reason to assume that this would start with a negative 10 instead of a 10, we're just going to say that this is 10. And we still have to find omega. So we know that the period is 4 seconds. And that is equal to the 2 pi over the omega. So we have to solve this for omega. So I'm going to multiply the omega to the other side and then divide by the 4. So we have 2 pi over 4, which is just pi over 2. So we have pi over 2 times t. T is our variable here. We don't plug in anything for t. But that is the equation for the simple harmonic motion of the ball over time. We also want to know the frequency. The frequency is just the reciprocal of the period. I'm going to write that out. So in this case, our frequency is 1/4. And what that means is that every second we go 1/4 of a period, which makes sense because the period is 4 seconds. But we don't have to write units on that, so you can just leave it like that, okay? All right, so let's try letter B. This time we are given the equation and we're supposed to find some of the details about this motion. So first of all, we want to know what's the maximum displacement. That's another way of saying the amplitude. So the amplitude here would be the absolute value of A, which would be the absolute value of 6, which is just 6. And I'm not given any units here, so it's just 6 some sort of units. Frequency is omega over 2 pi, which we know that omega is 3 pi over 4. So it's going to be 3 pi over 4 over 2 pi, which we could write as 3 pi over 4 times 1 over 2 pi. So the pi's cancel, and I get 3 over 8. So every second or whatever unit of time we're using, we go 3/8 of a period. The value of D when t equals 4. So for that, we would just straight up plug in 4 for t, figure out what our distance is when time is 4. So we have D equals 6 times cosine of 3 pi over 4 times 4, which is just 6 times the cosine of 3 pi. And the cosine of 3 pi, if we whip out our old friend, the unit circle, would be -1. So we end up with -6, which we could technically write units after. And then letter D, the least positive value of t for which D equals 0. So if we set D equal to 0, the formula was 6 cosine of 3 pi over 4t. We're going to try to solve this for t. So let's work through this here. So first we would divide both sides by 6. 0 divided by 6 is still 0. And then we think, okay, to get rid of a cosine, because now I can't kind of continue to isolate the t until I get rid of the cosine. So I'm going to have to take the inverse cosine of both sides. That's going to cancel out with this cosine and just leave me with the 3 pi over 4t. And the cosine inverse of 0, if we take a look at our graphic organizer from 5.3, you will see that that gives you a value of pi over 2. So we have pi over 2 equals 3 pi over 4t. And then to solve for t, I'm going to multiply by the reciprocal. So we have pi over 2 times 4 over 3 pi. Again, the pi's cancel, so we get 4/6, which is the same as 2/3. So that's the smallest positive value of t for which d equals 0. In the extra practice worksheet, you're going to see why this is the least positive value, and there are other ones. I mean, it makes sense, right? If we're bouncing up and down on a spring, there's going to be other times when the d is 0, when we're at like the equilibrium line. It doesn't only happen once, it happens several times. And using inverse cosine will only get us the first one. But there is a way to figure out the other ones, and that'll be something that you figure out in the extra practice, which will be the next thing you do after this. But anyway, thank you very much for watching. That is the end of the lesson. I hope you have a great day. Let me know if you have any questions.